Good afternoon, everyone, and welcome to the Civil and Environmental Engineering Distinguished Lecture. My name is Khaled Musallam. I am a professor of structural engineering, and I have the great honor and pleasure to introduce our distinguished speaker for this distinguished lecture for the spring of 2016, Professor Jack Moehle. I have about 5 pages written about Professor Moehle, but I'll try to be selective because I only have 5 minutes. So Professor Moehle joined UC Berkeley some 36 years ago, maybe you were 15 or something, in 1980. And he is the founding director of the Pacific Earthquake Engineering Research Center, a very important center in the state of California that I have the pleasure to be its current director. He is currently the T.Y. and Margaret Lynn Professor of Engineering. Professor Moehle's active research has several facets. They mostly focus on design and analysis of a structural system with emphasis on earthquake engineering, reinforced concrete, construction, new and existing buildings and infrastructure. One of the unique characteristics of Professor Moehle's research is he pays serious attention to professional design guidelines and the development of these guidelines. And because of that, he has been serving in several consultancy roles, and I will highlight a few of these that predominantly involve a peer review of several major projects. And these, the list is long, but some of the highlights are technical advisor for San Francisco Public Utility Commission, engineering criteria review board for San Francisco Bay Conservation and Development Commission, peer reviewer for peer seismic retrofit program, a very large program, and the Trans-Bay Transit Center, and many tall building designs. And I think we are going to hear some of that today in his lecture. Professor Moehle chairs the ACI Building Code Committee, very important in the profession and research and practice of design of concrete structures. He was a leading contributor to Caltrans design specifications, known as ATC 32, that emerged after Loma Prieta earthquake that involved significant changes in the Caltrans design specification. Also, he was a leading contributor to the seismic evaluation and retrofit standards, part of ASCE 41, performance-based design for new buildings, FEMA P 58, very important documents. He have authored or co-authored with his students and collaborators more than 350 publications. Recently, he has published an important textbook, on seismic design of reinforced concrete buildings. Jack's distinguished career is highlighted with so many awards that the list is very long, so I am not going to try to mention them all, several awards and recognitions. But again, I will highlight a few. He's an honorary member of the Structural Engineering Association of Northern California, and he also was the recipient of the first Helmut Klauwinkler award that's awarded by the same institution in 2015. He's a fellow of the American Concrete Institute, American Society of Civil Engineers, Structural Engineering Association of California. He's an elected member of the National Academy of Engineers of the United States in 2014, and he's also named Academico Corrispondente. I don't know if I said that right. This is from the Engineering Academy of Mexico in 2015. So with all these accomplishments, Jack is also happily married with 2 children. And I see Melissa sitting here and Erica also in the back. And I think one of the biggest rewards that Professor Moehle is still waiting for is to become a grandfather, and which is going to happen very soon. Probably you will be the youngest grandfather, but I'm sure you are excited for this new accomplishment that you are waiting for. And without further ado, Professor Moehle.
Thanks, Khaled. Very, very kind of you, and overly generous. Wow, to live in this place and to work in this place and to be able to teach in the San Francisco Bay Area and at the University of California, Berkeley. What greater thing could there be? And to see so many of my colleagues here and students and friends and family, it's really nice. But being in the Bay Area is the best place to be. And having this honor today is really very nice for me. I decided to talk about performance-based design, seismic design of tall buildings as a subject that I've been involved with for several years. And that I think is changing the cityscapes up and down the West Coast of the United States. And it's changing the way engineers are designing buildings and other structures. And so I thought I'd pick this topic and take it apart, try not to go into too much depth about it, but give a broad picture of what's going on and what I think is going to go on in the years ahead. And I do want to note some of the materials, a lot of the materials are going to focus on one project or maybe a couple projects. So I wanted to mention Magnus and Klemenchik Associates and Arup, who did some of the engineering work related to this, and also to acknowledge Computers and Structures, which has very generously given software to the university, which has enabled some of the work that we do here. And I see some folks from Computers and Structures are here today. We all look at the buildings and the construction of our current time in a special way, and we think that it's unique. But I bet the designer of that building in 1924 thought that that was really something special as it was built. And we can look as we go from left to right in the different eras how the construction has changed. It's gotten bigger, it's gotten more elegant in some ways, maybe not in all ways. And the construction and the abilities to do this kind of work has been driven in large part by structural engineers' ability to imagine the flow of forces or to use technology to calculate what structures are doing. And today, buildings designed in 2010 are designed with very sophisticated software. The performance is studied in great detail. The structure is modeled in the computer, and ground motions are input, and it's shaken, and we observe, not really, but we observe in the software what's really going on. Go back into the 1970s, and the software was much less advanced. We were mainly using linear computer programs at the time. But at that time, there were tremendous advances that were possible in construction because of the fact that the computer was available and enabling engineers to extend their thinking in design and construction. Now, 1936 was also a very important time in the structural engineers' development of computational procedures. No, definitely before the computer. But this fellow, Hardy Cross, was a professor at the University of Illinois. And Hardy Cross developed some very important analysis methods. One of them known as the moment distribution method. How many have heard of the moment distribution method? A few of you. And students have only heard of it because we tell them we don't teach it to them anymore. But it is instructive to see what Hardy-Cross had to say about it. The idea, if we had a beam across 3 supports, and we didn't know how to solve the problem, we could fix the rotation of the middle support, we could apply the loads, we know the solution for that case. We can find the imbalance in moments at these supports and say, let's use linear superposition and add a moment in the opposite direction and free this joint, so there it is. Voila, there's the solution. And this way of solving problems for structural engineers had a huge impact in structural engineering in the 1930s and 40s and 50s. It enabled engineers to design buildings and other structures as they couldn't have done before. I understand that Hardy-Cross also had some impact on hydraulics. Is that correct? I think so. I doubt if you're using Hardy-Cross methods there anymore either. Hardy-Cross also had some very interesting things to say about standardization. And that's a subject that ties in very closely with what I'm talking about today, performance-based design as opposed to standardization. And let's see what he had to say. He says, as the size and complexity of projects increased, it became desirable and even necessary to set up a series of routine procedures for analysis and design. Fair enough. With these standardized formulas and specifications and methods, it became possible to use a greater number of men, and men with less training to produce engineering works. Now, forgive me, those were Professor Cross's words. You have to understand it's 1952. To bracket my age a little bit, Khaled, I wasn't born yet, so you can't quite blame me for this one. At the time, most of the engineers were men. Berkeley was way ahead of the time, ahead of the times, of course. Julia Morgan, a very well-known architect and engineer, graduated from Cal in 1894. She was the only woman in the graduating class. But apparently Professor Cross didn't pay attention to what was going on in forward-thinking parts of the country. But what he says here, get over the men and women business, what he says in this line is it's kind of shocking. It allows it being possible to use a greater number of men and women with less training to produce engineering works. And one has to wonder, is that really what standardization is about? And in a way it is. In a way it is. And he writes then, as a check on fools and rascals, the fools, those who don't know so much, and the rascals, the ones who know a lot but want to get away with something, or set up as an intellectual assembly line has served well in the engineering world. And Hardy-Cross is very often quoted because of his mention of fools and rascals. But I think this statement about standardization is shocking. And I think we should think about the fact that standardization really, in a way, is set up so that engineers can do more with less knowledge, and it'll still be safe. And just think about it. I'm not promoting that as a way forward. I'm just commenting that that's what we might think of when we think about standardization and not being allowed to design outside of that standardization box. Now, standards work really great in the building industry for most of the construction. If you look at the construction that goes on in the United States, 93% 1 to 3 stories. Not very interesting to most of us, although there's some fascinating buildings in that group. 6% 4 to 13 stories. The 1% is 14 stories and taller. And the kinds of buildings that I'm mostly interested in talking about today are even a fraction within that 1%. It's a tiny fraction of the buildings. And it's natural that the standards that are written up are written mainly for the 93%. Right? Those are the buildings that are more routinely being designed. And as we squeeze into the 1%, the standards really don't work so well, at least in many cases for those buildings. And here's a smattering of some of the building projects that I've worked on over the years. And the top are the best buildings, the ones in Northern California. And down below is Southern California. But starting back 15 years ago or so, and then some projects that are still in the works today. The two buildings on the right, Salesforce Tower in San Francisco is under construction and was intended to be the tallest building on the West Coast, west of the Rockies. And then along came Wilshire Grand, which is about 20 feet taller. And so they've scooped the Salesforce folks, perhaps. But these are the kinds of buildings that I'm interested in mainly. And these buildings are different from what's typical in our written building codes, in our standardized codes. In the code, there are height limits for certain kinds of buildings. And a core wall building, a building that resists lateral loads solely by the core that the elevators and the stairs are in, is only allowed up about 15 stories or so, right? Depending on your story height, you might be able to squeeze it in there. These buildings are going up 60 stories tall, so they're way outside of the height range that the code was intended to be used for, the standardized part of the code. And then we're beginning to mix conventional systems cores with things like buckling restrained braces as outriggers. And these combinations of systems aren't recognized within the standardized code, and you pretty much have to design these by something different. The dynamics of these buildings is also different. Most buildings are designed thinking about a fundamental mode of response, but look at in the middle, the shear forces in the wall. It's almost all higher mode response that's driving the behavior of these and controlling what the design forces are. And we can't expect that a standardized building code that's written for the 99% of the buildings is going to be very effective in dealing with these buildings. And so starting in about 10, 12, 13 years ago, there began to be some pressure from the structural engineering community and architects and developers to design something outside the code that would be taller, more functional. And it was kind of the Wild West for a while because engineers had no guidance. One engineer would be designing a building one way across the street. The same engineer would be designing the same building. There would be peer review panels checking the work. And on one building, the peer review panel said, I'm not going to approve this building if you put that in there. And across the street, an almost identical building, a different peer review panel was saying, I'm not going to let you design the building if you don't put it in there. And so totally opposite views were being expressed about how to carry on this work. And so seeing an opportunity and, in fact, a need to move practice forward, we started about the time of the centennial of the 1906 earthquake. So around 2006, we started in the Peer Center a program to develop performance-based guidelines, ways to use analysis and testing and so forth to build these buildings that were taller and that would perform better in predictable ways, but with some organization, some guidance. And so I worked with practicing engineers from Seattle, Los Angeles, San Francisco, researchers up and down the West Coast, building officials. We pulled together a program worth about $2 million for analytical work and developing guidelines, and we published this in 2010. We had absolutely no authority to do this. We just did it. And we put it out there. And it was immediately picked up by practicing engineers, and it's become one of the more widely, probably the most widely used document for performance-based design of tall buildings, not just in the US, but around the world. I find this being used. And there are some competing documents. I think they stole most of what they have in the competing documents from this one. But that's neither here nor there. Moving practice forward is always good. So what am I talking about with performance-based design or prescriptive design, the other standardized way? Well, the prescriptive approach in a very simple single slide, because I don't have that much time here, you envision the model you're building, you create a linear model. There's a prescribed strength that's at 2/3 of what you think the maximum shaking might be. And then you take that 2/3 and you divide it by a number like 5. Because the code says you can. That's that R factor. You get there's some details that are required to be used. There's height limits imposed. And the owner of the building gets the engineer's stamp, but there's no information about what the building's going to do. None whatsoever. It's code compliant, and that's as much as you can say. The performance-based approach, in a very conceptual way, a single slide again, is thought of more in terms of how the structure physically behaves. And so one might think if you pushed a building slowly toward some collapsed state, damage gradually progresses in the structure. We can see that in the nonlinear force displacement curves. The graduate students are all learning about this, I think, this semester. And some have an exam on Thursday about this, I bet. We identify that there's some damage threshold somewhere there. And there's also some point where we become a little skittish about whether the building's going to be safe or not. Actually, calculating and predicting what the collapse is going to be is very difficult, and we haven't gotten there yet. It's in our future, I think, to get there. But we're not quite there yet. But we know how to analyze a structure up to the point before it gets into that state of degradation. And we set two limit states. One, it should be serviceable in some reasonable time frame. And two, it should have a margin against collapse for something that we think is the biggest that might ever happen. And so we pick the biggest event as something that's got like a 2,500-year return period. In coastal California, we like to live dangerously, and the risk is a little higher here where we're close to faults. But it's a very rare event that we're talking about. Now, the way the engineer goes about this process, and again, we'll just cover only on the surface, starts with looking at the ground motion. And we live in a very exciting part of the world here on the Berkeley campus. This is actually the fault map that URS used to determine what the seismic risk is, the hazard map should be for the UC Berkeley campus. So there's UC Berkeley shown there. The project I'm going to talk about, Salesforce Tower, is in San Francisco there, and it's a very rich seismic environment. Now, what's done in the seismic design of a building as a starting point here is to look at all the known faults and to think about what the fault segments are, what are the probabilities of individual segments going off or combinations of segments, what are the average long-term slip rates, and from that, what's the range of ground motions that you might get. And if you have more questions about this, one of our experts, like Professor Bray, would love to answer the question, I'm sure. But engineering seismologists and geotechnical engineers work on this problem. Once there's a sense of what the range of fault rupture might be, we use attenuation models that tell us how the ground motion attenuates from the source to the site. And a huge amount of work has been done on this subject by the Pacific Earthquake Engineering Research Center. Is Yusuf Bezorgnia in the house today? I think he may be traveling. But Yusuf had a tremendous amount of work related to this in the Peer Center, really using huge databases to figure out how to attenuate the ground motions from source to site. And the Peer models are really all that's used today in figuring out what the design ground motion is going to be. Now, there are site analyses, of course. We can estimate what the rock does. We can filter that through the ground. In the end, we end up with a response spectrum, which gives us a measure of how a structure that's linear would respond, in this case acceleration, as a function of its vibration period. Most structures that fit within the prescriptive provisions of the code are sitting back in the 1 second period range. The buildings we're talking about are off at 4, 5, 6, 7 seconds as their initial vibration period. So they're way out in the response spectrum. And this spectrum is used to define what the shaking intensity will be at a site. There are techniques for filtering ground motions to fit them to these particular periods. I'm a structural engineer, and so I chose, given time limits, not to cover all that. But ground motions are selected that are representative of the seismic hazard. And it would be at the low end as well as up at the high end of the hazard level. And it could be for long periods, for the fundamental period of vibration, and for shorter periods. And one of the key things that may be part of the setup for the ground motion is making sure the duration is long enough to excite the building and is representative of the hazard. If we're in the near field, like we are on the Berkeley campus, very close to an active fault, we would want to include an impulsive motion or a number of impulsive motions to excite the structure. And our geotechnical engineering faculty at Berkeley are among the top experts in working this field out. But this is a project, I think Professor Bray participated in the review in setting up some of the ground motions with Arup, who was the engineer of record on this. The structural side of it, we take the building as it exists and boil it down to something much simpler, a model of the structure, an analytical model, quite unlike what we do in the prescriptive code provisions where all we would model is the core. In the performance-based design of a building, we model all of the structure, everything that might affect the behavior of the structure and everything that might be affected by it. Okay, so we've got the core modeled. We would model the slab column framing connecting to that. Very complicated, detailed models of how the structure enters into the basement and is fixed into the ground. But the computational procedures today, for the most part, aren't sufficient to allow us to model both the structure and what the soil's doing in routine designs, even for these very tall buildings. So what we do is we generally fix the bathtub, the basement. We model the structure, do the calculations there, and then we come back and apply what we get from the superstructure back onto the foundation. There's still some advancement to go on there. The models are simple and yet very complicated. This is a typical load versus displacement response for a coupling beam. So we're modeling the full nonlinearity and the degradation that occurs at large deformations. And here's what a computer animation might look like as the ground motion starts. And it's very quiet, but it would be very noisy in that building. It's quite possible one would be seasick up at the top. But if you lived to tell your grandchildren about it, it would be okay. Now, these displacements are greatly amplified, okay? So it's not quite that bad. You're not going to be thrown out. But up at the top of Salesforce, one would anticipate the motion to be about 4 feet, plus or minus, not including whatever the ground rigid displacement is. So they're big movements. And seasick, probably, okay? And then one takes what one gets from the analysis. All sorts of things come out. You know, and one of these analyses takes about a day to run, just on the fastest computers we've got. It takes about a day just to run this darn thing. And we get shear forces, very concerned about shear forces in these core walls, because the core is supporting not just lateral load, but the vertical. So we want to be very sure to get this right. And we can't get this right if we use the prescriptive methods in our building codes. It's just not adequate. We look at what the strains are over the height of the building. And these are strains in the concrete or the rebar in compression or tension. And Professor Philippou, you might note the strains are very small in this. And so we may be yielding at some location up at the top where the core cuts back. The compressive strains are, in this case, well below what we would think to be spalling or crushing strains. These buildings don't develop very large longitudinal strain in the core walls, and that's a good thing. All right, it means the damage is likely to be somewhat lessened. Now, I mentioned we also do worry about what's going on in the foundation, and so what's done is to look at the moments that come in and the shears that come in from the core coming down onto the foundation mat. A typical practice is to plot orbitals of how that moment varies in different directions, and then to take that and apply that in other software to look at what the bearing stresses are, and also to examine what the stresses are and forces are in the concrete mat that supports this thing. Now, I have to give a little plug for large-scale structural testing, and it goes something like this. Shear in plain concrete has been studied for 100 years. But the early studies, and hundreds of them, of course, all used little specimens because you could build lots of them and you could test them easily. After enough of those were tested, and there were more, I got tired of drawing points. Somebody said, let's see if this scales. So they went to 2 feet thick, and things got a little weaker. And somebody said, well, if they're getting a little weaker, maybe we should try something thicker. And things looked like they stabilized, but it wasn't quite sure. The typical foundation mat for one of these buildings is 10, 12, 14, 18 feet thick. It's way out there where we haven't tested anything. How many have taken an undergraduate class in foundation design or concrete design? Some hands. How do we teach you how to design the footings? You make them thick enough so that you don't need shear reinforcement, right? And all the theories that we've been using for years are maybe not quite right. Professor Collins at the University of Toronto just finished a big test. That's a full-scale person, but their silhouette. This is a almost 13-foot thick segment of plain concrete. It's only about a foot thick, so it's deceptive. But this is kind of what we're looking at in terms of failure of these things. And notice the cracks that are marked. At the bottom where the beam is in tension, the cracks are very closely spaced, and they're relatively narrow. As we move up through the height, the cracks tend to all branch together into relatively few cracks. And so the width of the cracks is greater. And this is a problem that happens as the member gets thicker. The performance that you measure in something shallow doesn't scale. So the wider cracks that occur upstairs mean that the aggregate don't lock together in the same way, and the unit strength goes down. So what did Professor Collins get? There it is. Where's it going to land? There. Okay. Way down there. Now, fortunately, there were researchers involved with this problem, advising cities about the possibility that this might happen. And we changed practice in these tall buildings, requiring that all of these be designed with shear reinforcement. And when we put shear reinforcement in these things, we know that the problem goes away. So there's a guy in one of these mats. We'll return to him later. Okay. So, what are some of the benefits of performance-based design as I've described so far? Well, we get a better understanding of performance. What's the real response to earthquakes? We get a greater assurance that the basic performance objectives will be met. But remember, all we did when we look at this is we say, well, let's make sure that the performance is serviceable for moderate quakes and that it doesn't show collapse for something big. Where can we go from here? Well, there's lots of places we can go. If we come back to this figure about performance-based earthquake engineering, in 2001, we invited Bill Holmes to a peer meeting and said, where can we take this? What can we do next? And Bill said, well, what you really ought to be doing is talking about performance of buildings, not in terms of cracks and crushing and spalling and so forth. You should be talking about what it costs to fix the building, what's the casualty rate, how long is the building going to be down. And so we undertook an effort in peer to try and figure this thing out. And you start at one end and you say, well, what's the decision variable? Well, maybe it's money. Money for repair cost depends on damage. Damage depends on how the structure responds. Here, how the structure responds depends on the ground motion. And then we've got models for what the ground motion is. Well, this is a very neat little problem to break up into 4 pieces because you can get the experts in each discipline working on what they're best at. One of the guys working in this came up with this little formula. The Peer triple integral based on total probability theorem. And love it. Our social scientists in the project in the center looked at this and said, this is oversimplifying the problem. And anyway, the real problem with this is to integrate this for real structures is almost impossible. And so I got an idea and worked with one of my students. I got a deadline is what I got. And said, look, we can pick a ground motion. We can analyze a building once. We can find what the drifts are. We can go to a fragility curve, something that tells us what the damage is given that drift. We can then add up all the damage that has occurred and figure out what it's going to cost, and then we can solve this problem. Big problem is, though, it takes about a day to run one of these tall buildings. And you need hundreds or thousands of these analyses to get enough statistics to know what the answers are. And so that didn't work. So we decided to try to do it statistically. And I worked with Professor Der Karagian. Very glad he was around to help figure this problem out. He said, oh, we can just do this with statistics and generate solutions. He says, but you're going to have to be careful because, as you know, when a building vibrates, is it going to move? Yes. The movement at one level is correlated with the movement at the other level. Okay, you can't just grab statistics on one level and forget about the other. You have to get their correlations sorted out and keep track of that. And thankfully, Professor Der Karagian knew how to do it. And so we incorporated what he gave us. And the idea was that if your responses are logarithmically distributed, if you take the log, you get a normally distributed variable. You can run through some simple MATLAB routines. I learned who Mr. Cholesky was, and back out, take the exponent, and you can statistically reproduce what analyses would give you if you have at least a sampling of what the results are. And this is like how fast it goes. And so by the time I'm done with my talk, we'd have our 1,000 analyses done, even on a 60-story tall building. So we can get the correlations all organized and do it sensibly. And then we can start talking about what happens in frequent earthquakes, rare earthquakes, really rare earthquakes, what's the cost? You can integrate over a hazard curve to get an annual frequency of costing so much. And then you can start making some better decisions about performance of a building. So we did one study looking at 9 different buildings. But here's just a pair. We did a standard design by the code and another design that was performance-based. We hired real engineers who designed these buildings. We hired a cost estimator, told us what it would cost. And there's good reason why the developers like these buildings. That's $6 million they can put in somebody's pocket, their pocket, right? And then we run through this kind of a routine and calculate what's the mean loss that you get out of these buildings. And lo and behold, the performance-based design, the one that you save money on, does better. And so there's really a return on this. So one of the questions I ask myself, well, what's next? Is we really need to make more out of this kind of analysis capability. Now, we gave this software to the Federal Emergency Management Agency, and they incorporated this in their ATC 58 performance methodology. And so this is now available, and engineers are starting to use this, not just with repair costs, but downtime and casualty. So it's out there. And I think it's going to start moving the profession into some different thinking. Once you calculate the repair costs, you can also find out where they are. And so you can begin to think about optimizing your design so that you can reduce the losses and the elements that are giving you the greatest loss. In this example, the slab column framing, which is just the gravity framing, is where all the costs are. Anyway, too much. Where else can we go with this? Well, maybe we should start thinking about the kinds of structural systems that we design. Current design is based on ideas that have been around for 50 years. And they use more or less conventional framing There are yielding zones in the conventional frames. We detail them so that they can survive the motions that are input. But you get damage, like concrete crushing or member yielding. You also get the problem that if the earthquake stops here, that's where you end up, with a big residual drift. Maybe we can do something a little better than that. And so there have been some ideas developed, lots of ideas out there on self-centering systems, and systems that maybe have replaceable fuses in them. Like this is one example that the Tipping Mar down the hill, now Tipping Associates, developed and has tried using in some buildings where you pre-stress the wall. You could have some replaceable fuses in these zones to dissipate some energy. When this yields, it simply rocks about the base, and then the pre-stressing clamps it back so it pulls it back straight again. So you get this kind of a force displacement curve and theoretically end up back at zero drift, which is pretty important. So we said, hey, let's figure out if we can actually do this. Does it really work in practice? And you can do this at a small scale. You can do it on a computer. There's nothing like doing it full scale on a shaking table. So we went to Japan. We'll play it again. But what you got here is two nearly identical buildings, full scale. This is the conventional concrete. You can see the damage that's occurred there. Uh-oh. Let's do it the manual way. But this is one of the ground motions, the Takatori motion, measured in Japan during the Kobe earthquake at 60% of its full intensity. By the way, we sit next to a fault, not so unlike what did this. This is 60%. Good thing, because some engineers are starting to use systems like this. Never yet for a really tall building, but for some moderately tall things in San Francisco. The Public Utilities Commission headquarters, some of you know about this building. It's performance-based design, self-centering walls, and sustainable concrete. I think they replaced 70% of the cement with fly ash in this system. So sustainable all the way around. So where do we need to go? In this field, we need to go more in this direction with systems that perform better. I have like four or five little what's next things. The first was the calculation of performance. The second was better performing systems. The third is what's next in terms of the buildings that we're going to be running into. And this is our past. This is the kind of building that we're used to, because you learn, you crawl first, and then you run, and then you end up there. Why are engineers designing these crazy things? Does anybody know? Architects want them, that's one reason. Who's in CE 120? Anybody in here in my class? Why do we make buildings that have curves or irregular surfaces? Yeah, the wind doesn't like those irregular things. Great. I'll remember you. And here's a simulation of a rectangular section. And look how the vortices go around, up the whole height uniformly. that really sucks a building to the side. And then the vortices go back and forth. Very uncomfortable building to be in. Look at that one. The irregularity fools the wind, and the occupants are much happier. Whoever said the architect wants it, that's really the reason why it goes that way. But this is what we're going to come up against. And the analysis and the simulation of these things is going to be much more challenging as we go forward. The other buildings we understood intuitively. We were just confirming what we thought we understood. Here, it's much more difficult to understand what's going on, and we're going to have better software to handle these things with greater confidence. The Disney building was performance-based design by a graduate from Berkeley. Look at this one. It was planned to go right next to it, another Frank Gehry design. Unfortunately, it was 2007, and the market crashed, and this building disappeared. But it was a fascinating one to work on for a little while. What's this? It's the wrapper from Los Angeles. And this thing is, I think, ugly. I think it's terribly ugly. And you wonder, where's the structural system? Well, if you take a look from this side, you can actually find something that looks a little bit like a coupled shear wall buried inside of it. So it's got some conventional things. This design has no columns. Everything is in these strips, which I have heard they're thinking about 3D printing in some way. I don't know how you do this in concrete, but it's fascinating to imagine a 3D printing of reinforced concrete construction. That's, I think, what's next is going to be moving in these fascinating directions. And then the fourth thing about risk categories for tall buildings. This looks too detailed. But in our codes, we have category 1, barns, right? Chicken coops. Category 4, critical functions like fire stations, schools that are important but not essential. And then everything else fits here. So like this building, only 150 people can be in here. This doesn't become one of these 300 or more. So this is where this building falls. Where do you think a tall building, 80 stories tall, falls? Risk category 2. Automatically, because the occupancy never gets above about 5,000. And typically it's 2,000, 3,000 people in one of those buildings. So they don't get bumped into this high occupancy unless they have a big auditorium associated with them where there's 300 people in one room. And so it begs the question. What's different about a tall building that we should be thinking about? Well, how about 10 tons of Trump landing on your building? Okay? That doesn't sound very appealing. What about all the cladding that's on this building? You know, we design it to stick to the building like scales on a fish. But they've got to stick there for the maximum ground motions that we anticipate we might get. And that's really important that we get there with that. Here's this is an engineer's rendering of a building. And suppose the building has residual drift of 1%. After the next big earthquake, and it's surrounded by a bunch of green tagged buildings. Well, maybe if the residual drift is 1%, it's a risk to the surrounding buildings, and everything around it gets green tagged, red tagged suddenly. We maybe shouldn't be designing individual buildings as individual buildings, but as members of a community. And here's San Francisco. Look at just one of those buildings arbitrarily. What's there? Well, there's easily 5,000 people within reach of every one of these buildings. And yet we don't design them that way in our codes. In San Francisco, there's some thinking starting about resilience in our cities. I had the fun and the pleasure of working with engineers and urban planners in this project, trying to brainstorm where should we be in designing our cities going forward. And we guessed at where we are in different kinds of residencies. What's the time to restoration? What we thought was a reasonable target. And to get there, because there's so much existing construction, maybe we need to aim our new buildings at something higher than that. We've got the tools to do it now. We've got performance-based engineering and all those things that we talked about. We don't have the research to support this. This is just somebody's thinking. And this is another thing going forward that I think we as a community need to spend time on, is quantifying and verifying these things as what we should be targeting as we move forward. Back to this guy. He's still in there. I think he got out eventually. But I think it's fun just to look as an engineer who works on these projects. It's fun to watch how these actually get built. So here's some quick photos. This is what's in a conventional core today. This is the one Rincon Tower. Those are real people down there. And here's a building going up month by month. And I think it's wonderful to be able to see how these are built. And they're built in a way that the core goes up first. It looks unstable until the rest of the building comes along. But in reality, the core is holding the rest of the building up, of course. And so one group, one union works on this part of the building, and then the next union starts down there. So now you've got people working in 2 shifts, and then that catches up. Eventually, somebody starts putting, not yet. There we go. Another group comes in and starts putting the cladding up on the building and begins working. And now you've got several crews working simultaneously on the same project. And it goes up, and it tops out in December, January, February, and March. And there's the full building. So it takes over a year to get one of these built. And it's fascinating to me to see how the construction actually is done. But equally important, what we're building is not just buildings for their own sake. We're putting buildings together for the people who live in them and the people who work in them and the economies that they support, the houses they support for people who live in there. And the entire community is really depending on these buildings to function properly. And so I think as designers and as engineers and researchers, we should be thinking about how these big buildings fit into our big cities. They're not just isolated buildings anymore. They're something special. And I think they should be designed differently. Closing slide. Here we are in Berkeley, looking back on one of the greatest cities in the world. We are at a unique time, I think, in the civil engineering field, in earthquake engineering. We can make a big difference in how that city survives the next earthquake. And I think it's going to come through advances in simulation. It's going to come through testing of unique systems. It's going to have to come through new sustainable concretes and other materials that we develop. It's going to have to come through people who are thinking about how the city as a whole works and how our part as structural engineers and civil engineers fit into it. With that, I'll leave you with those thoughts, and thank you for your attention. Professor Moehle, what do I do? Do I ask for questions?
They won't ask you a question.
Sure. I'd be glad for questions. Yes, Carl.
More people live in old buildings than in the new buildings. How are we going to deal with the upgrading of the existing infrastructure in San Francisco? That's really the challenge, it seems.
Right. No, it's a great question. The real hazards, the risks are in the older building stock. And I've done some work, as you may know, related to older concrete buildings. And we had selected the city of Los Angeles as a study area. And through reasons that kind of got out of my control, the information got out of the inventory that we were collecting. And that, in that particular case, it was like an earthquake happened in that city without it ever happening. And subsequent to that, there have been some revisions in the thinking, and there have been some regulations that are developed related to that problem. But it's a problem that's going to be haunting us and with us for many years. San Francisco has the older, the tuck-under parking residential wood construction, the multi-family wood frame construction is probably the biggest hazard right now. And so San Francisco has undertaken programs that are in the news on a routine basis to handle those structures. Many of the older unreinforced masonry buildings have been retrofitted. Whether adequately or not, I'm not the judge on that. We're kind of holding off a little bit on the older concrete buildings because there's only so much I think a city and its populations can handle. But the real risk right now lies with the older construction. There are retrofitting methods that are available, but they're costly in many cases. And for the most part, the residents of the city don't really know what kind of risk they're facing. I think they should all be forced to sit and watch that video of 60% of the Kobe earthquake ground motion and then say, no, I don't want to fix my building. I think the occupants of Davis Hall should be thinking the same thing. Great question. Yes?
So as San Francisco stands right now, say if the big one hits, and it's like a magnitude 9 point something.
Go higher, 10.
How much do you think would still be standing after that?
It's a great question. How much would still be standing? I think a lot would still be standing. I think among the best group of buildings are the ones that are being designed by these procedures because to the extent possible in the computer analyses, we are representing the real behavior of the building and the real ground motions we anticipate and demonstrating that those buildings, at least to the best that we can do it with our software today and our knowledge today, those are going to be good. I think those are the best buildings out there. The buildings that were built since roughly 1980 or so, I think tend to be pretty good, but there are some weaknesses in the building stock. Your question really is what kind of losses might we expect in a big earthquake? I hope not a magnitude 9, but we could get 7, 8 or so. And the estimated losses for the city run something like $150, $200 billion. They're very high. We can take as an example what happened to the city of Christchurch in New Zealand, a much smaller community, hit by a smaller magnitude earthquake, but strong shaking nonetheless. And that city has almost been destroyed because so many buildings were damaged and so many buildings had to be removed that the city doesn't really exist anymore as the one that I used to know from 15, 20 years ago. What would happen in this city if there's a magnitude 7.8 earthquake and it's going in the wrong direction? Rather than racing away from San Francisco, it's racing toward it with a big impulse of motion. I think it could be a real disaster. And there have been studies of this as part of the 1906, the centennial of the 1906 earthquake, and estimates of $150, $200 billion and thousands of lives lost. And that's really without looking at what the community losses can be. The SPUR study and the SPUR effort is really to try and recognize that it's one thing to keep your building standing, but it's totally another to keep your community vibrant. And if people can't go back into their homes, they can't go to work. And if the businesses are shuttered, then they have to go somewhere else. And it takes a long, long time for a city to recover from that. So it's better to work on that now than after. Yes?
So Jack, at the end of your talk, you gave a view of what's next.
So given the, for research, given the limited resources we have for research, what would be the first thing you start with amongst the list you gave us?
Wow, the first thing, I think the first thing to start with is developing an understanding of how an individual building fits in a community. And doing some simple studies to to understand what can be done to improve the function of a tall building as it relates to the community in which it sits. I think that's one of the most important things right now that needs to be done. There's lots of other things. We're in the lab now working on high-strength reinforcement. Very important. But there's much bigger picture things, I think, related to resilience, sustainability, and addressing what kinds of new buildings and systems and design methods need to be developed so that those buildings will help make our cities more resilient and sustainable going forward.
Professor Moehle, thanks for the excellent talk. Back here.
Yes, okay.
My question is related to Professor Piester's in a way. Today you primarily focus, as I understood it, on high-performance design in the pre-construction phase. I'm curious about high-performance monitoring in the post-construction phase. Can you talk about that and how you see that in the future?
Okay, yes. So I see it as an important part of our future. In my own way, I see it through earthquake engineering. And in many of these buildings, there is seismic instrumentation going in. And that instrumentation can be used to inform the city about which buildings in which buildings have the properties changed in some substantial way, such that there is the potential for damage, and that could lead to more rapid inspection methods and so forth. But I think that going forward, I think in a smart city, there's not just knowledge about what happens after an earthquake, but we should be able to monitor what the health of a building is. Day in, day out, is it operating in the most sustainable way given the weather conditions that are prevalent today, given the occupancy that we have today and what else is going on. So I think instrumentation in dealing with the huge amounts of data that are going to come out of our large cities is going to be a really important aspect going forward.
Hi, Professor. So kind of piggybacking off of that last question, I was wondering kind of in the during construction phase for these very tall buildings, are there any extra considerations for the building you showed that was in construction if an earthquake hit when it was halfway up? Is there any special concern there?
There is, and I have always questioned those considerations in some ways. In the design of a building, it's designed considering it has a certain life to it. And so the life spans a long enough time frame that the intensity of events, shaking events and wind events and so forth, that should be considered in its design broadens. But in the construction phase, the construction maybe lasts 1 year. There are some design methods that suggest, well, one really only needs to look at what's the performance during 1 year of service life of the construction. And so I think if there are efforts taken to secure construction sites and to make reasonably sure that they're safe should an earthquake occur. But I think if we think about buildings as members of a bigger community, there's always construction going on, and the life of construction really is much longer in many ways. And I think longer time frames ought to be considered for dealing with safety in those structures. But there is some consideration, yes. I'm getting a Holly timeout.
Well, since we're getting close to the reception time, we already exceeded that, so please join me in thanking Professor Moehle one more time.